Hello, and welcome to your third lecture on recurrent neural networks. But actually, today we're going to take a little break from learning about different recurrent architectures, and we're going to talk a little bit about text processing. In the examples that we've looked at in the previous two lectures, we often talk about the fact that recurrent architectures are used often for things like machine translation or generating sequences of text. But computers can't necessarily understand words. Instead, we'll have to get them into a format that computers can actually understand. And that involves a lot of concepts and steps that we'll talk about today. Let's walk through the basic process that it takes for us to take actual written text and get it into a form that a computer can actually understand through something like a recurrent neural network. The first thing might be pretty obvious when you think about it. When we get in a piece of text, we need to standardize it to get rid of some of the quirks that happen when written text, for instance, capitalization or different modes of punctuation. For instance, in this sentence, the word the appears multiple times, but the first time we see it in the original sentence, it's actually with a capital T, and we might want to standardize it to communicate to the computer that these are the same word, despite the fact that in the original sentence, technically there's a capital letter. Once we take our sentence and standardize it, we then need to break it down into what are called tokens. Tokens are individual units for analysis, and typically we think of tokens as words, where each token in our analysis is an individual word. However, there's nothing stopping us from having individual characters be tokens or larger sequences of words, which is actually something we'll talk about a little bit later. So we've taken an input sentence, we've standardized it, and now we've broken it down into individual units called tokens. But of course, like I mentioned, the computers don't really understand words. They understand numbers. And if we're going to feed all of this input into something like a neural network, we're going to have to take these tokens and turn them into numbers. One way to do that that's really easy is with one-hot encoded vectors. One-hot encoded vectors are very similar to dummy variables. They're really sparse vectors of zeros and ones, where 1 indicates which word we're referring to. For instance, in this vector that you see on the screen, you can see the different lists of words. Here we have a vector where there is a 1 at the word the. This means that we are referring to the word the. Similarly, if we wanted to refer to the word sat, we would put a 1 in this position. And if we wanted to refer to the word that, we would put a 1 here. So we finally have a way to take words, standardize them, process them into tokens, and now compute them into vectors of numbers that our computer or neural network can actually understand. In real life, these vectors are going to be huge because there needs to be one entry for every possible word in our entire vocabulary. So these one-hot encoded vectors could actually have tens of thousands of different possible entries. This is a very high-dimensional vector. But even if we have tens of thousands of words represented in these one-hot encoded vectors, we know that there are more words than that actually exist and could come up in our text. For instance, if we take this sentence that we've been looking at, the cat in the hat sat at the table and ate a bat, and replaced one of the words with a word we've never seen before, that could pose a problem for these one-hot encoded vectors. For instance, let's say we change the sentence to be the cat in the hat sat at the table and ate a platypus, or Perry the platypus. So if we have the word platypus now, and this isn't a word that is represented in our one-hot encoded vectors, how do we encode this new word? Well, the short answer is we really can't. There's no entry in this vector for the word platypus, so we don't have a way of telling a computer that that's the word that is occurring here. What we can do is we can add a new token or entry that represents an unknown word, something that we're not familiar with that's not in our vocabulary. Here we have a 1 here with this unknown token that indicates to us that we do have a word here, but it's not a word that is in our vocabulary. Okay, so to review the steps we've talked about, we take an input text. We need to first standardize it, get rid of things like punctuation and capitalization that make words that are actually the same seem different. Then we take that standardized text and we convert it into tokens. While we could use individual characters as tokens or actually longer sequences of words like 2 words or 10 words, typically tokens will mean an individual word. But of course, computers and neural networks need numbers, not text, as input. We then take these tokens and convert them into one-hot encoded vectors of zeros and ones. And while that's the general process, I wanted to talk about a few miscellaneous text processing topics that will come in handy as you're processing your own text data. The first concept is stems. Stems are a way of taking words that have the same root and representing them the same way in a sentence. For instance, in this sentence, it says, "I was sitting on the bench and I thought that it was a nice place to sit and think about life." Here, we see 2 examples of a same root word being used slightly differently in the same sentence. For example, we have the word sitting as well as the word sit in this sentence. And in many cases, it might be useful for us to encode that while they're different tenses, these 2 words are really representing the same concept, the concept of sitting. In order to do this, we can replace words with their stems being a shortened version of what they have in common. For instance, here, we can replace both sitting and sit with the stem sit to represent the fact that even though they're different forms of the word, these both refer to the fact that we are sitting. Similarly, we have the word thought and think in this sentence. Both of those could have the same stem word of think to represent the fact that we are talking about the same concept despite we have slightly different forms of the word. Next, let's talk about the idea of a bag of words. Text processing is very complicated, but for a lot of things that we do with text, like topic modeling, we actually don't need to consider the sequential nature of the words that are being used. While recurrent neural networks are truly sequential models, other types of text-related analysis does not require that we assume that the text that we have is sequential. Bag of words refers to times when we are thinking of text not as an actual sequence, but of a collection of words whose order does not really matter. For example, with the sentence, "The cat in the hat sat at the table and ate a bat," we could think of that as a collection of words where their order doesn't really matter. They're just jumbled together in a bag that represents, for instance, the topic of the document that we're talking about. This goes along with the idea that we can process text as either a sequence where the order does matter, which is how things like recurrent neural networks treat text, or we can treat it as a set, where we're just looking at a collection of words without really considering their order. If you're interested, something we're not going to cover in this class, but is very common in text analysis, is latent Dirichlet allocation, which is a topic modeling model that considers text as a bag of words. Okay, I did a little bit mislead you to the fact that bag of words have to discredit all order in a sequence. We actually can encode some order in our sequence by using something called n-grams. N-grams are collections of sets of words that we get by sliding a window over a text. For instance, n is just a variable, so I could look at a 2-gram. A 2-gram means we're going to look at every collection of words that is too long or shorter. For instance, as I take this window of 2 and slide it across my sentence, I get all of these pairs of 2 words that I move through sequentially in my sentence. Here's the end result of looking at all the 2-grams in my sentence. You can see it's every individual word, but also every collection of 2 words that I got as I slid my 2 window over the entire sequence. This allows us to encode a little bit of positional information about our data. Even though we could still take all of these words and treat them as a bag of words, we are still giving ourselves a little bit of context for each of the words by, at least in this case, looking at the word before and after it. And nothing's stopping us from looking at higher ends, for instance, 3 grams, 4 grams, 5 grams, etc. The next concept we'll talk about is TF-IDF, or Term Frequency Inverse Document Frequency. TF-IDF is a way of weighting words both by how frequently they occur in a specific document, therefore telling you how important that is to the topic the document's about, while also considering that some words are common across all documents, like I and the. To calculate the TF-IDF, we have to calculate both the term frequency and the inverse document frequency. Term frequency, like the name implies, is basically a count of how many times a word occurs in a given text, divided by the total number of words. For instance, we could look at a text like the book Jane Eyre and look at how many times the word Jane appears. Next, we need to calculate the inverse document frequency. This basically looks at how many different documents in our collection that this word appears in. The more often a word appears in other documents, the less information it actually gives us about our specific text. For instance, like we talked about before, the word and appears in pretty much every document and probably occurs pretty often, but because it occurs in every document, it doesn't really give us much specific information about an individual document. When we multiply the term frequency and the inverse document frequency together, we get our TF-IDF. When words are fairly common in one document but not common overall, it tells us that that word gives us a lot of information about the topic of that document. For instance, even though the word and might appear a lot in a document, it also appears in a lot of documents and therefore is a little bit less important. However, a word like apple, which might appear a lot in a recipe for apple pie and doesn't appear in a lot of other recipes, does tell us a lot about that individual document. Next, let's talk a little bit about cosine similarity. Cosine similarity is a similarity metric that measures the similarity between two vectors by looking at the cosine of the angle between them. According to cosine similarity, vectors that are close together in terms of their angle are similar. This is important in text processing because often we have all those one-hot encoded vectors that we talked about. If we add all of the one-hot encoded vectors for every word in a document, we basically get a vector of word counts. We could look at the similarity between two documents by looking at the cosine similarity of their vector of word count. However, we still want to know the similarity between two documents, even if one is longer. For instance, imagine you wrote an article about machine learning, and I wrote an article that's twice as long about machine learning. Even though my word counts will be higher, according to cosine similarity, our word count vectors would probably be very close together, even though, for instance, mine might be this long and yours might be this long. Because of the way that cosine similarity looks at the angle between vectors, we would still consider these two documents to be very similar. While it's not super on topic for what we're talking about, I think another cool application of this could be in something like retail marketing. We might want to compare different customers based on their purchases and their pattern of purchases specifically. For instance, we might work at a Sephora and we want to know people who are buying mostly things like skincare and perfume versus people who are buying mostly things like foundation and eyeshadow and lipstick. Even if two customers are different in the amount of things they purchase, we still might want to know that they have similar patterns, like that they mostly buy lipstick and only rarely buy face wash. So again, cosine similarity works as a way to measure the similarity between two vectors by looking at the angle between them. Even if one vector has higher values overall, if they're similar in their direction and pattern, then two vectors will be very similar. We can use this, of course, on vectors of word counts for individual documents to see if they're similar. All right, let's get to the main topic here, word embeddings. So far, when we've looked at text, we've converted them into one-hot encoded vectors as a way to represent an individual word. However, these one-hot encoded vectors have a few problems, one of which is that they're going to be incredibly highly dimensional because we need to have one possible entry for every single word in our vocabulary. They also have the disadvantage that two words that are similar, like book and novel, aren't really similar in the way that they're represented. In comes word embedding. Word embeddings are vectors of numbers that help represent a word, sort of like a one-hot encoded vector, but with some desirable properties that we'll talk about in a minute. One advantage of word embeddings is they tend to be a little bit lower dimensional than those one-hot encoded vectors. Word embeddings might look a little something like this, where the word gorgeous is represented by this vector. And the word Python is represented by this vector. So that sounds really nice, but how do we actually get those vectors? Well, it turns out that we get them with neural networks. In order to create a word embedding, we actually create a fake problem that we don't really care to solve, but we'll output these embeddings as a byproduct. In the case of Word2Vec, which is a very common word embedding, we are going to pretend that we want to solve the problem of creating a neural network that fills in the blank of a word in a sentence. In solving this problem, we're going to use context to learn the different word embeddings. And of course, these word embeddings are just a byproduct of solving this fake problem of creating a neural network to fill in the blank. Let's look at this sentence here. The cat ate. We can take this sentence and we can create a neural network that can predict what a word is based on the surrounding words. For instance, here, let's pretend that cat is the blank word. So we want to use the words the and ate as input and have our model learn to be able to predict the correct word, the blank word, cat. To do this, we can create a neural network. For instance, in this simple case, we are using only the word right before and the word right after the blank as input. We input these into the neural network as one-hot encoded vectors. Then we feed them through a hidden layer, and we can decide how big we want this hidden layer to be. The output of this network is going to be a vector of probabilities for which word it thinks should fill in the blank. Of course, we would like this to output the highest probability for the actual word, cat. And while this type of task is a little bit new, the structure of this neural network should be very familiar to you. Now, of course, like I mentioned, we don't actually care that our neural network can perform this task of filling in the blank. What we really want is this hidden layer in the middle of our network. This layer is generating the embeddings that we actually care about. This is why choosing the dimension of your hidden layer is important, because that will be the dimension of your word embeddings. The bigger you make your hidden layer, the higher dimensional your word embeddings will be. So to review, we can take a neural network and basically solve a fake problem of trying to guess which word should go in the blank in a fill in the blank. We input the context words, in this case just one word before and one word after, as one-hot encoded vectors. We send them through a hidden layer, and eventually we output what we hope is a predicted probability where it guesses the correct word to fill in the blank. But we don't really care about the actual output of this network. What we're after is these embeddings that come from our hidden layer. Now, there's actually two ways that people will design these networks that produce our embeddings. The first one that we just did is a continuous bag of words. The continuous bag of words does what we just did. It tries to predict a blank or a target word based on the context of the words around it. The other way that we could build our network in order to generate these embeddings is using the skipgram method. In a skipgram, we're actually trying to predict the context words based on a target word. For instance, taking our same sentence, the cat ate, we might put the word cat as a one-hot encoded vector into our model and want it to output both the and ate. We're putting in the target word and we're asking it to generate what the context words are around it. Even though we have a slightly different structure to our neural network, what we're after is still that hidden layer, which is going to give us the embeddings for our different words that consider the context of words around it. Here's the word embedding for the word king, based on the glove model, which, like Word2Vec, is a very famous word embedding model. You can see that the hidden layer in this network was very long, so we have this very long word embedding to represent the word king. We often do need high dimensional embedding so that we have more flexibility for words to be similar to each other in different dimensions. Basically, the more dimensions we have, the more flexibility a vector has to be similar to one word or another. And when we represent words with their word embeddings, we get some really cool properties that we can use. For instance, let's consider these four words: king, queen, man, and woman. Remember that points on a graph can basically represent a vector that moves from the origin to that point. And one thing to note about all of these vectors is that relatively they're pretty close together. And this makes sense because all four of these vectors are representing people. One nice thing we can do with word embeddings, at least if they work properly, is that we can do vector algebra with our different words. For instance, here we can see the same vector that gets us from king all the way to queen is the exact same vector that gets us from man to woman. Essentially, this vector is representing gender, or at least the change in gender from going from man to woman. Another cool thing we can do with vector algebra with these word embeddings is subtract them. This vector here represents the word king vector minus the word man vector. Semantically, we can think of this as saying, take the concept of king, but subtract out the gender of being a man. Colloquially, we might represent this concept as royalty because the difference between a king and a man is the royal nature of that person. The cool thing about word embeddings is we can take this vector that essentially represents royalty, king minus man, and we can add the vector woman. So we're saying, take the concept of king, subtract the gender of being a man, and add back the gender of being a woman. When we do this, we actually end up with the vector queen. And this makes sense. When we take the concept of king, subtract being a man, and add being a woman, the concept that results is the concept of being a queen. To give you another example, let's look at the comparison between king and man and queen and woman. We already said that when we go from man to king, we're basically adding the concept of royalty, and this royalty vector is the same one that takes us from woman to queen, because when we take a woman and add the concept of royalty, we get a queen. And just like before, we can take the concept of queen, subtract the concept of woman to get this vector, and then add the man vector to result in the word king. So again, we took the concept of queen, subtracted the concept of being a woman, and added the concept of being a man to get the vector king. Another thing that's nice about these word embeddings is that words that semantically mean things that are similar to each other should be very close to each other in the embedding space. Now, of course, our embedding space is going to be a lot higher dimensional than this two-dimensional example I have here. But even here, we can see clusters of words like neat, tidy, and clean, all being in the same region because they refer to very similar concepts. Similarly here, we have a group of words like unkempt, gross, and messy. These are all very similar to each other and therefore close to each other, but are very far away from neat, clean, and tidy because they mean very different things. Now, we talked a little bit about Word2Vec and GloVe, which are two very common word embedding models. We could also always build our own embedded model, whether on its own or as a part of a neural network that we're training. These embeddings take our one-hot encoded vectors, which we created by standardizing, tokenizing, and then one-hot encoding our text, and turn them into vectors that are no longer sparse, they're no longer full of zeros, but that represent the semantic meaning of a word. These embeddings will typically have really nice properties, such as the ability to do all that vector algebra that we talked about before, and certainly that words that mean similar things will be near each other or have very similar embeddings. All right, that's all I have for you. I will see you next time.